Thank you, Thomas, for the introduction. So my name is Abhinav Kohar. I'm a machine learning solutions manager for Schlumberger. I head the AI portfolio for Schlumberger for the Americas. Me and my team work on a variety of machine learning use cases, be it computer vision, natural language processing, prognostics and health management, time series forecasting, and the like. On the top, you can basically see a QR code. If you want to connect with me on LinkedIn, you can scan that. And today I'll talk about AI and Internet of Things for operational efficiency and production. So first, Schlumberger has rebranded itself into SLB, driving energy innovation for a balanced planet. So you don't have to pronounce the complicated Schlumberger anymore. It's very simple, SLB. All right. And this is the agenda for today. So first, we'll talk about the challenge of using AI and IoT to monitor satellite field wells for operational efficiency and production. Then we'll talk about a platform solution which runs a machine learning algorithm at the edge to classify Dynacards and enable smart alerts that proactively notify users if anomalies are found when monitoring the data. And finally, we'll talk about the results, one of them being reduced anomaly downtime up to 70% for the connected wells. So most of the satellite fields are in remote locations and they are not digitized. They lack the infrastructure for collecting the data and basically artificial lift optimization. And that is where edge and advanced analytics come into picture. So the manual data collection on these fields lead to two kinds of problems. First is insufficient and discrete data for any post-failure analysis. And second, minimal data to investigate pre-failure events. We need real-time monitoring to prevent well downtime and production loss. So what does a satellite field looks like? It has rod pumps, which are the most common form of artificial lift for oil wells. Today, these systems are used to lift formation fluids from more than 600,000 wells worldwide. A rod pump system consists of a prime mover, a surface pump, a sucker rod string, and a downhole pump. The overwhelming majority of the surface units are beam pumps. So you can see a sucker rod pump right here. And what is a Dynacard? Dynacard is simply a plot between the load and displacement over a pump cycle for a sucker rod pump. And it is critical in order to analyze the health of a downhole pump. And the shape of the card is basically used to tell what is the health of the pump. And a proper and detailed analysis of Dynacards can help in reducing the pumping cost, equipment failure, appropriate selection of pumping equipment, and increase in production. So if you see here, there are some sample shapes for the Dynacard available. So this is the normal pump operating conditions, the ideal card. This is basically the slanted normal condition. This is fluid pound, gas interference, and finally worn out pump. And these are just some sample shapes. We also have more than these. So in the past, we were periodic and reactive to do well intervention. And for some satellite fields, it could take up to months in order to get permit approvals. But today, we are continuous and predictive, monitoring all these wells in real time and diagnosing them. So this is what the pre-Internet of Things and artificial intelligence workflow looks like. First, we'll mobilize a team for the site. Second, they'll get permit approvals, which can take a long time. Then they'll manually go to the remote location, record the Dynacards. They'll come back to the office, share it over the email with the team. Then we'll use a software to visualize these Dynacards. Finally, it will be sent to the subject matter experts, and they will basically tell what is wrong at the site. And finally, they'll send this information to the maintenance team. So you can see there is a long cycle here, and the data available is discrete. And sometimes it is very hard to basically predict failures before they happen. So what do we need? We need this new data flow architecture to avoid all these problems. So these satellite fields do not have any existing infra for getting the data. So one of the requirements is that in order to digitize these fields, it should be economical. And second, we should be able to send this data to the cloud, which will enable machine learning and AI on this particular data. And so this is the satellite field. And we are able to collect data from this field using the controllers. And this data is basically sent to the rod lift optimizer from Agora. And this, through a cellular network, basically sends it to the cloud. And this is just an IoT gateway. and Agora is a SLB subsidiary company. So you can see with very economical setup, we are able to send this data to the cloud, which will basically power our platform. So the first thing in this platform is a data visualization layer. We can visualize the Dynacards in real time and interpret them. So here you can see a time lapse of Dynacards plotted over one another, and this basically tells me how the pump health is evolving over time. Second, we can also visualize the field status. We can check which wells are over pumping, under pumping, optimally pumping, and adjust our strategy accordingly. We can also visualize a lot of sucker rod pump parameters. We can visualize the motor current, the strokes per minute, the Dynacard area, pump fillage, and this basically also tells you about your pump health. And finally, since we have so many Dynacards being generated every single day, thousands of them, it is not possible anymore to rely on our subject matter experts to basically tell us what it means or what is the situation at the pump currently. So we basically need a machine learning algorithm which can basically tell us what kind of failure is happening at the pump and how to diagnose that. So here we can take a look at sample failures, the normal pump operating conditions, high fluid level, very high fluid level, and gas interference. And on the right-hand side, you can basically see sample data distribution for these classes for a particular well. And as you can see, this is an imbalanced class problem for machine learning to handle. So what we did was we sent all these particular labels to our subject matter experts. This is also part of the platform. They tagged all these Dynacards with different classes, normal operation, high fluid level, and all the others. And we fed this through a neural network, and we were able to predict basically with a very high accuracy, 80 to 85% for different wells, what kind of failure is going to happen at a particular pump. And this was basically used to send smart alarms to the maintenance team. And this was also deployed at the edge so that we can do the predictions in real time, and we don't need to send all the data to the cloud because it requires a lot of bandwidth, and we can save some bandwidth with the help of that. And finally, we also deployed this using an end-to-end machine learning pipeline, which consists of 6 stages. The first one is basically the orchestrated experiment. Second one being the continuous integration of building, testing, and deploying the packages. And then third one is the continuous delivery. Fourth one is the automated triggering of the pipeline. Fifth one is basically the model delivery or model serving. And then we have the performance monitoring. And based on this, we can trigger the pipeline again. And as you can see here, this above part is basically for the experimentation or development phase. And this one is for staging and production phase. We also provide an ability for our subject matter experts to fine-tune the model. So we are predicting basically thousands of times a day the pump health. And if the subject matter experts feel that something is not correct or something is changing at the pump, they can basically change the tags, and this will be fed again into our machine learning pipeline for retraining, and the model will be updated in an online learning fashion. And as you might know, that the model health keeps on decaying with time. No model is perfect, and the performance will degrade. So we basically have automated triggers to retrain the model based on 2 things. One is the F1 score. So if the F1 scores goes down below, say, threshold tau, will basically re-trigger the training. And second is basically when a data drift happens. So data drift is basically a covariate shift in your data. So based on a combination of these 2 factors, we'll re-trigger a training. And this will keep your pumps in, basically your models, pump models in evergreen health. And now is the time to discuss the results. We'll discuss downtime reduction, we'll discuss the smart alarms, and sucker rod pump optimization based on this platform for the satellite fields. So downtime reduction. In the first graph, you can basically see the Dynacard area on this axis and strokes per minute on this axis over time. So here when the failure event A happens, basically you can see the Dynacard area drops, the strokes per minute drops, and it takes the team around 60 hours to basically bring the pump back online. But after the deployment of this new infrastructure, we are able to generate an algo-based alert before this event happens, and the team is able to bring the pump back online in less than 6 hours. So you can see there is an order of magnitude reduction in the downtime. And yeah, this is very, very useful for all our wells. Secondly, we are able to send these smart alarms before a catastrophic failure happens to the maintenance team. And they are able to take preemptive actions in order to normalize the pump conditions. And the smart alarm algorithm is based on the moving average of the card area, Dynacard area. And this is the overall algorithm. And next, we go to sucker rod pump optimization based on the platform. So on the left-hand side, you can basically see low pump fillage based on the Dynacard area. And the well was ramped down in order to basically prevent failure. And finally, after some time, we are able to ramp up the well, and we can see normal operating conditions of using the Dynacards. And if you kept on operating the pump basically at off condition, this would lead to catastrophic failure. So we are able to reduce downtime here as well. And on the second hand side, here you can see another optimization. So basically, we have high gas interference and high friction in the pump. This sometimes happens due to debris or residue in crude oil. So the subject matter expert was able to see this on the platform, and he recommended a hot water circulation through the pump. And after that was done, we were able to improve fillage and reduce the friction. And this again prevented a catastrophic failure at the pump. So you can see this economical infrastructure using an edge IoT gateway, and this platform allows us to digitize our satellite fields, and we are able to prevent failures, increase efficiency, and basically prevent failures. So that is my time, and now I'll open up for some questions.
If you would like to ask a question, could I just ask you to raise your hand so I can bring the microphone to you?
How many data points are required for retraining?
That's a very good question. So for retraining, you need to keep a few things in mind. How much is your data size? Say 10 million data points versus 1 million data points versus 10,000 data points. Second is basically data drift, which we talked about, a covariate shift in your data distribution. And third is basically the frequency of updates, like how frequently do you get new data? Do you get new data every 1 month, every second, every nanosecond? And based on that, you can use different strategies for retraining. You can have a fixed window strategy for retraining, which basically means you just say use the new data to retrain, forget about the past. A dynamic window strategy, where say you have 100,000 data points, you get new 5,000 data points. You can keep those 5,000 data points as test data, the other 100,000 as basically training data, and use like a grid search or something to find the window size and basically retrain. Or you can use a representative subsample selection, where your training data looks like production data and you train on that. But in all these strategies, you need to be mindful that you do not have data drift or concept drift. So yeah.
Sorry, you had your hand up? Yeah, I did.
Thank you. Good presentation. Do you have a comment on the cost of the system versus the savings?
So the cost of this system is basically, the edge IoT gateway, which we basically put on the field, where we have a controller, and that basically, it has everything, a cellular network to send your data and everything. And basically, the platform is available on the cloud. So that is the entire cost of the system. And the dollar amount basically depends on your usage. So that is a little different. And the savings, as we saw, is basically, 70% downtime reduction and 85% reduction in failure. So that is like millions of dollars of savings with respect to the cost of this infrastructure.
Okay, I guess just to follow on, but isn't there the cost when you add those systems, the people to manage and generate the models, which you would not be a cost if you didn't have those systems? So
yeah. So as we talked about, right, the people are only required in the beginning when we deploy basically the box, and after that everything is automated. So we talked about the model. The model is already automated, and the retraining is automated through the ML pipeline. If your model performance degrades, say for a particular field, it will automatically get new data from that particular field, retrain itself. And apart from that, there is no involvement from our side on this particular field unless, say there is a client support required or something like that. And the subject matter experts at the particular field can just visualize what is going on. So, and they can also like trigger a retrain manually that, hey, this doesn't look correct, and I'll basically change some labels, trigger a retraining, and that's it. So there is not a lot of involvement from our side, and most of this is automated. All right. Thank you, everyone.